Thank you for introduction. I'm Takao Murakami at ISM, and today I'd like to talk about a location trace anonymization contest. We organized this contest in 2019, so here I will explain how to design such a contest, and I will also report our contest results. Okay. So first, I will explain the outline of this work. Recently, a large amount of location traces are collected into an LBS provider, and they are useful for various types of geodata analysis, such as distribution estimation and modeling human mobility patterns. And to protect user privacy, the LBS provider needs to anonymize location traces before providing them to a third party. But there are several challenges in location trace anonymization. First, long traces are very hard to anonymize because locations are highly correlated with each other. So there are no conclusive answers on how to anonymize long traces. It's still an open question. And second, there are two types of privacy risks: ID disclosure and attribute disclosure. In the case of locations, ID disclosure is caused by re-identification attacks. And attribute disclosure is caused by trace inference, which infers the whole locations in the original traces. And they are two major risks in location privacy, but their relationship is still unclear. For example, suppose that algorithm A is secure against ID disclosure. Is it secure against attribute disclosure? Or conversely, suppose that A is secure against attribute disclosure. Is it secure against ID disclosure? In this work, we focus on these research questions. And to answer these questions, we organized a location trace anonymization contest called PWS Cup 2019. The feature of our contest is that both defense and attack compete together, which is close to what happens in real life. By doing so, we can find empirically good anonymization methods. And also, our contest evaluates the relationship between ID disclosure and attribute disclosure. And regarding the relationship between two risks, we first show that the security against ID disclosure doesn't imply the security against attribute disclosure. We show a strong counterexample to this direction. And then we show through our contest that 2 implies 1. So we believe that our finding provides a guideline on how to anonymize traces to achieve both 1 and 2. For example, one promising approach would be to make traces secure against trace inference, because it would imply the security against re-identification. Okay, so next I will explain PWS Cup and related work. PWS Cup is annually held in Japan, and in this contest, both defense and attack compete together to find a good anonymization method. And it's also useful for an educational purpose, such as improving anonymization skills. And in 2019, we organized a location trace anonymization contest. So related work closest to ours would be differential privacy temporal map challenge by NIST. In this challenge, participants could compete for a differentially private algorithm for short trace, such as 7 locations, or coarse-grained locations, such as 78 regions. And our contest differs from the NIST challenge in 2 ways. First, we deal with a long trace with fine-grained locations. We deal with 400 locations and 1,024 regions. So this would be much more challenging. And second, we evaluate both ID disclosure and attribute disclosure. And we believe that this is also a major difference. Okay, so next I will explain how to design our contest. First of all, we assume that the LBS provider anonymized traces. The LBS provider provides anonymized traces to a third party for geodata analysis. And the third party is an honest but curious adversary, and he knows reference traces. The reference traces are separated from original traces, but are highly correlated with original traces. So this is called the partial knowledge attacker model. So we assume that the adversary doesn't know original traces, because otherwise trace inference doesn't make sense. So this is a contest flow. First, each team obfuscates his original traces by adding noise, generalization, or deleting some locations. And then, based on the anonymized traces, we calculate a utility score, SU. SU takes a value between 0 and 1, and a higher value means higher utility. And then, based on reference traces, other teams attempt privacy attacks, such as re-identification and trace inference. And based on the results, we calculate a re-identification score, SR, and trace inference score, ST. They also take a value between 0 and 1, and higher value means higher privacy. And SR and ST are the lowest scores among all the other teams, so we evaluate the worst case privacy. And we require each team to have SU larger than a threshold SREC. So all the anonymized traces have high utility. And then we decide a winner based on privacy scores, SR and ST. Okay, so, and here is a detail of utility and privacy scores. For utility score SU, we use a versatile utility score to enable various types of geodata analysis. Specifically, for each original location, we calculate the Euclidean distance d between original and obfuscated locations. Then we normalize the Euclidean distance d to a score between 0 and 1 using this piecewise linear function. And finally, we calculate SU as the average score over all original locations. And for privacy scores SR and ST, we use the average metrics for simplicity. So for a re-identification score SR, we use 1 minus re-identification rate. And for trace inference score ST, we use the normalized Euclidean distance. Here, we use the opposite score function like this to ensure that a higher value means higher privacy. Okay. And for data set, we note that public data sets cannot be directly used. This is because if we use public data sets, every team would know the original traces of other teams. And this will violate our assumption of the partial knowledge attacker model. So to address this issue, we generate synthetic data with diversity. Here, we randomly generated traces of virtual users. The virtual users have their own features, such as always staying at home or sometimes going to the office. And the virtual users' features are different for each team. And to have such diversity, we extended the location synthesizer in our previous work. And we distributed original traces to each team, and we published only the reference traces. So each team doesn't know original traces of other teams. So this is a partial knowledge attacker model. Okay, so next I will explain our contest results. Before our contest, we conducted some preliminary experiments to show some examples of obfuscation. So we implemented some sample obfuscation algorithms proposed by previous works and evaluated their privacy. And here we have the results. Black dot represents no obfuscation, which doesn't obfuscate traces at all. So this is just pseudonymization. And we can see that the cheating anonymization is secure against re-identification attacks, but it's not secure against trace inference. So this means that high SR doesn't imply high ST. And to explain this issue, we explain the cheating anonymization method. This anonymization method selects P% of all users and randomly shuffles their traces before pseudonymization. So for example, if P is 100, we shuffle all traces before pseudonymization. And then we do pseudonymization. So the random shuffle here is location obfuscation. It's not pseudonymization. Then what happens? The anonymized traces give no information about user IDs because traces are randomly shuffled before pseudonymization. So the re-identification would fail like this. But the anonymized traces have too much information about original traces. So trace inference would be perfectly done like this. So this is an example of obfuscation, secure against re-identification and not secure against trace inference. And based on this result, our contest gave an award to a team that achieves the highest trace inference score, ST. So all teams did their best to achieve high trace inference score, ST. And here we have the results. We can see there is a strong correlation between SR and ST. So this means that high ST implies high SR. And the best algorithm uses a technique somewhat similar to K-anonymity, but we omit detail for lack of time. So for more details, please see our paper or ask questions. Okay, so let me summarize this talk. In our work, we showed that 2 implies 1 through our contest. So one promising approach would be to make traces secure against trace inference because it implies security against re-identification. And for future work, we'd like to use stronger privacy metrics than average metrics. And another important future work would be to use application-tailored utility metrics, such as errors in aggregate time series. Okay, so thank you for attention.
So thank you very much for the talks. Is there a question in the audience? Maybe I can start. So you talk about the best anonymization, but what about the best attack? Can you say a few words about how it works? Or?
Yeah, so here is the details of the best anonymization algorithm and best attack algorithm. And basically, best anonymization algorithm calculates a feature called a visit count vector for each trace. And the visit count vector is composed of a count for each region. So in this example, user 1's vector is 2102, and they apply k-means clustering. And then they add small noise to regions so that visit count vectors are similar within each cluster. So this is somewhat similar to k-anonymity, but it doesn't provide strict k-anonymity because the visit count vectors can be slightly different within each cluster. Yeah. I think this algorithm provides the best performance because strict k-anonymity and differential privacy destroy utility for very long traces. Yeah.
And for the attack?
For attack, it also uses a visit count vector. And it calculates a visit count vector for each user by counting each location fuzily. So, for example, if a user visits X13, we normally add 1 to X13. This is row counting. But here, fuzzy counting adds 0.2 to X13 and 0.12 to X14. So it's count each location fuzzily. And then it re-identifies users or infer traces by using the visit count vectors as features. And by using fuzzy counting, the visit count vectors will be more robust to small noise in the original traces. So I think that's why this algorithm provided the best performance.
Thank you very much. So we can take a question while we switch computer. We check if there is a... So we don't have a question on Zulip. Anybody in the room? No. Okay, so maybe we can thank you again and
Okay.
go to the next speaker.
Thank you.